Okay, so today you had just finished going through a graphing worksheet that allowed us to graph the relationship between the three variables for our gases that we're going to focus on more specifically, just like in the gas station investigation labs. We had the three variables, which of course were pressure, which we mark as P, volume, which we mark as V, and temperature, which we mark as T. All right. And so in order to make sure that we can identify relationships and establish what happens when you change one and how does it affect another, we have to have only two changing at a time where the third is held constant. And that is going to be identified by these three laws. And really, it's just taking one of the variables and again, holding it to where it does not change. And so in this case, we have Boyle's law. You won't necessarily have to know them by name, but knowing the relationship between the variables that are changing. The constant variable here is temperature, which means that pressure and volume are what we are focusing on there for Boyle's law. So if you look at this example, there are ways that you can just calculate these individually, but we have actually a combined law that we'll do that with, and I'll talk about that there. So what you notice here is that we're only focused on pressure and volume changing. We are assuming that, again, T is constant. So because it's constant, it doesn't change, which means that we don't need to necessarily worry about it for this relationship. But what we notice is as our volume increases, well, we're not going to be able to collide with the walls as frequently here in this balloon. And therefore, if the collisions goes down, that means that the pressure is going down. And so we have an inverse relationship here. It is our only inverse relationship as well, pressure and volume. And I like to think of it as VIP, thinking volume is inverse of pressure. What does that look like graphing? Well, we based off of our graphing worksheet, we can see that an inverse relationship would look something like this, where as the x-axis grows in a quantity or value magnitude, we see that the y-axis goes down, right? So they do opposite. So that's why we identify the inverse relationship as that. Then we have, of course, Charles' law, and Charles' law is when pressure is held constant. So think of this as all of the flexible containers, right? When volume is changing in some capacity, that means that the container that the gas is in is able to expand and contract. And so in this case, we see that volume and temperature are going to be the two variables that we focus on here. So identifying what happens, well, now, the faster the particles are moving on average, which is what the temperature measures, the more collisions they're going to have with the walls. Think of your human gas particle activity. And then when you cool them off, right, now they're moving slower. So you have, fast particles compared to slow particles. Those slow particles are not going to be able to take up as much space, which of course allows the container to decrease in volume, right? And so we have our relationship here where pressure is constant, and the pressure being held constant is happening by the container itself, right? In order to keep that pressure the same, if I'm cooling something down, well, then it's going to have a smaller space in order to have more collisions, correct? If you heat things up then, right, if we were to go backwards, then that would mean that the pressure, in order to be constant, now that the particles are moving faster, well, I have to give them more room to operate so that they have the same number of collisions or force of collisions on average compared to what we had before. And of course, this is a direct relationship. We know that as one variable goes up, the other does the same. As one variable goes down, the other goes down as well. And so anytime we have a direct relationship, our graph looks something like that. All right, something like that, where one axis is increasing in magnitude or value, and the other one does as well. Depending upon what you have, does not necessarily matter what's on what axis, pressure or, volume or temperature. And last but not least, we have Gay-Lussac's law, and this one is when, of course, we're keeping the volume constant, right? So now this would be like those pressure apparatuses that we were using in class, where you're submerging that little metal bulb into into either hot or cold water, and by doing that, not allowing the volume to increase or decrease, right? Not allowing that to expand or contract, then allows us to get a really good relationship between pressure and temperature. Right, pressure and temperature, and identifying that when these particles are moving slow, they're not going to hit as frequently. They're not going to hit those container walls, so that pressure is going to be lower compared to when they are heating up, right? Then that means that they're moving faster, which means more collisions, right? And so in terms of what this value P would be, if we were actually to calculate this, and that goes for any of these relationships, if we were to calculate the value, well, depending upon what happens to the other variable for these last two relationships, the third, or the variable in question is going to do exactly the same thing, right? Directly related. It makes sense that the faster I have those particles moving, the more collisions they're going to occur. So this one is where volume is constant. And again, it is a direct relationship. And therefore, we have a graph that, again, would look something like this, right? So now there are graphs. You can see the only one that's inverse is Boyle's law, again, identifying the relationship between pressure and volume. If you wanted to make a shorthand version of kind of what's happening at the particles level for all of these, in these specific cases, right, given these initial and final conditions, right, all of these are initial, right, what the gas starts at, and final conditions. And so we can take these, and then I'll just duplicate them, just so you know that there's a start and an end to all these, a start and an end. That's how we're able to calculate or compare variable changes. So in this case, it would be, the volume is increasing, right? Volume goes up, which means there's more space, which means less collisions, which then, of course, means less pressure, right? And so if we were to calculate this value of pressure, we would notice that it would be lower than the original, and that's because now the particles have the same space to operate, and they're moving at the same speed on average because temperature is constant. In this example, for our Charles law, we see that we're decreasing the temperature, right? And if temperature goes down, then we are moving slower, right? So slower particles. And slower particles, then they take up less space because they move closer together. And if they move closer together, then of course the volume is going to go down. So you can kind of see that what's happening at the particle level helps us understand this relationship a little bit better. So the last one for Gay-Lussac's law, when volume is constant, now is in this example, as we increase temperature, that means that the particles are moving faster. So we say faster particles, and just like in the human gas particle activity, faster particles means more collisions with the container walls, more force is being exerted on those container walls more frequently, and therefore pressure goes up. And so we can kind of identify why the Boyle's law relationship over here is the only inverse relationship compared to the other two where they are directly related. And so that brings us to our combined gas law. Now, a combined gas law kind of takes all three of these laws up here and puts their relationships into a mathematical representation where we can use all three variables at once. And the cool part about it is this equation works even if a variable is either, let's say, not included, or it's missing, or it is told to us that it is constant, right? And so, of course, this combines the relationships between pressure, volume, and temperature. What is a constant? It is a variable that remains unchanged. All right. So in a problem like this, we say that for a constant variable, it remains unchanged, and we can either one of two things: told it is constant in a problem. So we're told that it is constant, or it is, or not mentioned in the problem. All right, and we'll take a look at an example of what that means. But a variable that remains unchanged, we're either told that it's constant or it's not mentioned in the problem at all. And therefore, we can just eliminate that variable in our equation itself. The initial and final units should match, right? And so if we have milliliters for volume here, well, then milliliters should be over here, right? If this is ATM, then there's ATM, right? This is always going to be Kelvin. No, write that there. Temperature is always in Kelvin. Again, that's because we cannot have a negative temperature according to Kelvin. So we don't use negatives. All right. And so just make sure that we're identifying the variables that we have, and we're identifying what we're looking for. So what I would usually do is I would take these problems, and I would either label, or even better, do both, write an inventory of all of these starting and ending values, and then identify X, basically, right? And we've done something similar to this before. So reading in context, a sample of gas occupies this many milliliters at this pressure and temperature. So because it's occupying it right now, we know that that is the starting condition, which means that this is a initial volume. This is a initial pressure, and then this is a initial temperature. And of course, it's already in Kelvin, so we don't have to do any conversions. It doesn't specify pressure or versus volume conversion. So the only thing it does say is that make sure that the new volume is calculated in milliliters, which of course is going to be the case because we have milliliters to start. So really we're not doing any conversions. We're just identifying what we want in the end. We see that we're looking for the new volume, which is X. And then we have our second pressure here, which is our changed pressure, and then, of course, our second temperature. So we're just plugging these in to these values here. So we got 75 milliliters there. We have 291 Kelvin. We have 725 millimeters mercury. We know that we are changing to 800 millimeters mercury for pressure, and we have an increase in temperature slightly from 291 to 298 Kelvin. So what does this look like? It is just using the above equation. Now notice all variables are mentioned in some capacity, which means, and nothing was told that it was constant, so we have to use the entirety of the formula. So here's P1 V1 over T1 equals P2 V2 over T2. And then we're just plugging in what we know and what we don't know. In terms of the pressure 1, we have 725 millimeters mercury at 75 milliliters of volume, 291 Kelvin here. And then that's equal to 800 times X, which is what we're looking for. And we have 298 Kelvin there. And so all we have to do is cross multiply. So you cross multiply, and you end up with everything kind of on one even line. And so let's do this in the calculator here. So let's simplify these sides. I'm going to do the yellow side first, or whatever side has all of the numbers, not the variable. So this is 725 times 75 times 298. That gives us a pretty big number. And it's okay. Don't be intimidated by big numbers. They are perfectly normal. So I'm going to write this out in its entirety, and that's going to be equal to whatever 800 times 291 times x is. So 232,800 times x. And of course, we just divide through by what's being multiplied to our variable there. And x, of course, is volume here. And we have 750 divided by our answer. And we get a decimal instead. And this would be 69.6 milliliters, of course. Correct the units based on the variable that we were looking for. And so does this make sense? Well, I know that the pressure went up as well as the temperature. Now, it's going to be interesting to identify these all at once, but if pressure goes up, then that means that, of course, that the volume should go down. That's based off of what we know about those relationships. And even though temperature increases as well, which would cause volume to increase, the change in pressure is greater than the change in temperature, which is why ultimately our volume is less than what we started with. So that's another reason why we don't like changing more than one variable and seeing how it affects one other variable. We like to keep one constant, but that's what happens when you change all of those. So let's do a couple more, and just to get a good idea of how to complete these calculations, and then you should be good to go on your own. So a sample of gas has a volume of this at standard temperature and pressure. Remember, standard temperature and pressure means that we have our value of 1 atmosphere and 273 Kelvin. All right, and so even though it doesn't tell me the standard, the temperature and pressure, we know what standard temperature and pressure are, so we can use those. So I'm going to do my nice little inventory here to keep track of my variables. And in this case, we are using atmospheres instead of millimeters mercury, and we are using liters instead of milliliters. And so it asks me to find the volume in liters in the end. So we are looking for the secondary volume again, because we have 1 atmosphere and it's increasing to 3 atmospheres of pressure. We have an initial volume of 8.25 liters. Our initial temperature is standard temperature, which is 273 Kelvin, and it is increasing to 293 Kelvin. All right, and so we use our equation, P1 times V1 over T1 equals P2 times V2 over T2. P1 we know is 1 atmosphere, volume 1 is 8.25, all over 273 Kelvin, times 3, an X on top, and then we have 293 there. So I do the same thing, just cross multiply. I like to multiply the side of the equation that has no variable first, so we have 8.25 times 293, right? Ignore the 1. 2417.25, and this is going to be 273 times 3, which is 819x. Divide through by what's associated with the variable that you're looking for. So we have 2,417.25 divided by 819. That gives us an x value of 2.95. And what is that? That is liters, because I was looking for V2. It asked me to find it in liters, and my original volume was in liters, so that tells me I just have to calculate it, and then that value is just going to be whatever I end up with in liters. In terms of something to keep an eye out for, we'll do one more example together here. Then you'll be on your own. The other two these other two problems will be on the key for the notes that you can do and check. And we'll probably do example problems there next class. But in terms of the number 3 here, we notice that we're given a temperature initially of 25 degrees Celsius, and that should alarm you because we cannot use Celsius in this equation. Therefore, we need to convert our degrees Celsius into Kelvin. Remember, Kelvin equals whatever my degrees Celsius is plus 273. Therefore, 25 plus 273. All right, and that's going to give us 298 Kelvin. So this is the temperature that we want to use in our actual problem, not the 25 degrees Celsius. That is a common mistake. So let's limit that from happening. So let's do an inventory. I love an inventory. It makes everything a little bit easier because when I know what I have and where everything goes based on the equation, I can just kind of plug it in and solve. We're looking for the new temperature, all right? So we're looking for T2 this time. We have 3.75 milliliters of space being occupied. And on top of this, what you should note is we have 2 different units of volume here, right? And so realistically, it doesn't matter which unit you use unless it specifies. For me, I like using liters just because that's kind of like the standard unit, the base unit. And because of that, what I'm going to do is I'm just going to convert the milliliters to liters. And you can do either way, really. It truly doesn't matter. So instead of the 3.75 milliliters, I'm actually just going to move this over 3 spaces to the left because, of course, there's 1,000 milliliters in 1 liter. So this would actually be 0.00375 liters. And so we're just taking that, moving it back 3 spots because of the 1,000. Then we increase it all the way up to 4 liters. All right. And then we go to our pressure. Our pressure is 1.15 atmosphere. We know that our initial temperature is 298 Kelvin, not 25 degrees Celsius. Again, converted that. And then our final pressure is 1 atmosphere. So it's going to standard pressure. And so we solve P1 times V1 over T1 equals P2 times V2 over T2. Plug in what you know. I know 1.15 atmosphere is what I'm starting with. 0.00375 liters there over 298 Kelvin is equal to 1 atmosphere, 4 liters, and X. All right, we don't know what that second temperature is. So whatever color coding system you want to use does not matter to me. If you want to color code at all or just circle. And we have, let's do 298 times 4, and that's going to be 92, right? I just do all of the one that doesn't have the variable first. 1.15 times 0.00375. That gives me 0.0043. Let's just do 125x. 0.0043, 125. 0.0043, 125. X equals 1,192 divided by that value. And what that is in decimal form is 276,405.79. For some reason, I think that probably should have been liters in general and not milliliters to begin with. because that is quite the temperature change in terms of this. But, well, we can do that too. Let's do this. Let's leave it. So at least we kind of have the idea, right? Obviously, this is an incredibly large number, and the way that this is written out, I'm sure that this should have been liters to begin with. But again, to stay consistent, just making sure that we threw in a unit conversion there, which is totally fine. So this would, this is way too big of a temperature change, but I guess it makes sense if the volume has gone up that much while the pressure is going down as well. So those collisions with the walls are going down slightly, but the amount of space that these particles are taking up must mean that they're moving really fast, as you can see. So going through again, it's kind of like a weird question there. So I'm sure that was just a typo, but hey, it is what it is, right? There it is. So the principle of how to solve these doesn't change. What I will say is these examples that we've done up to this point are they include all three variables on both sides. For something like this, let's say that we weren't given the volume in this problem, right? Let's say that volume didn't exist in this problem. Well, what we could do is we could still set this up for everything if you want to remain consistent. And then all you would note is because it's not mentioned, or if it says volume is constant, well, just get rid of volume in general. And now you're just comparing P1 and T1 to P2 and T2. And so instead of our equation looking like this, right, like our combined gas law as a whole, well, we're just taking away volume. Right, and we can solve the same way. We don't have to worry about a volume, right? And so when you start getting into other problems like that, that's going to be helpful there to identify. Hey, this is being told to me that it's constant. This is not mentioned at all, so that means that I can just ignore it because it's not going to change from start to finish. So that's how you do those types of problems. But other than that. I hope this helps at least get you started with these, with using the combined gas law and identifying these relationships between values. All right. So if you have any questions separately, just let me know. And other than that, I will see you later.